Hello everybody, welcome back to another lecture. This week we're going to start a new module in the course. This module is going to be focusing on acoustics and it's going to last for 2 weeks. This week is going to be a basic introduction and overview, look at sound and what acoustics really is, and then next week is going to focus on how we implement design strategies into our designs that will control acoustics. All right. So your readings for this week are going to be the acoustics chapter from the Ballast textbook. I will have that posted to the Blackboard module folder, and then chapter 7 from the Bengali textbook. All right, so let's get started. When designing, it is common to overlook acoustical treatment. However, proper acoustical treatment is important because poor acoustics can make spaces unpleasant to be in or even unusable. Okay, so let's say you have an office or something like that and you're trying to get some work done. Obviously, if too much sound is coming into that space, wherever the source is, maybe it's people around you or maybe it's sound from the outside like cars and stuff going down the street. If you have too much sound in the space, it could be distracting and the space could even be unusable because you just can't get any work done, right? The space can't be used then in an efficient way for what it was intended. So interior designers are responsible for selecting equipment, materials, finishes that have an impact on the acoustical performance of a space. Therefore, designers should understand properties of acoustics so they can make informed design decisions. This chapter will provide a basic introduction to the properties of sound, and the next chapter will focus on design strategies that are related to acoustics. All right, so for this module, really, this is going to be kind of a survey of acoustics in design strategies, just to get you introduced to it and familiar with the topic. But later on, you will be taking a class that is going to be solely focused on acoustics and design strategies for acoustics, okay? So we're just going to get you introduced here so that later on when you take the full course on this, you will have a just good, solid base understanding of what the terminology is. All right, so let's talk about some sound basics. All right, so sound, that can be technically defined as rapid fluctuations in air pressure. Okay, so anytime we hear sound being transmitted, whether it be through the air or through another medium like water, the thing that is creating that sound is just changes in pressure within the air, okay? So sound can be defined as a physical wave, as a mechanical vibration, or as a series of pressure variations in an elastic medium, okay? So the elastic medium, that would be whatever the sound is traveling through. So if it's traveling through the air or through a material like concrete, like a building material, or water is another medium. And then whenever you hear sound referred to, especially in the textbook, they're going to be referring to that as a mechanical vibration. For sound to exist, the following three things must be true. All right, there has to be a source, there has to be a transmission path, and there has to be a receiver. So something has to create a sound. That sound has to have a way to make it to somebody who can hear it, and then there has to be somebody who can hear it, okay? So if you think back to kind of the old, I guess, phrase or adage, if a tree falls in the middle of a forest and nobody is there to hear it, does it actually make a sound? Technically, according to this definition, no, it doesn't make a sound because there's nobody there to receive the sound that's being transmitted. All right, sound propagation. So sound waves are mechanical waves, unlike light and electricity waves, which are electromagnetic. Okay, so we've been talking about heat and electricity and all those types of currents and waves, in the past. And those were all electrical or electromagnetic waves, but these are all going to be mechanical. So there's a little bit of a difference there. Amplitude, this is commonly referred to as loudness or volume. When you think of turning up the volume on a speaker, for example, that would be synonymous with amplitude. And that is going to be a measurement of a sound's wave from the lowest point, that being the trough, to its highest point, being the peak or the crest. All right, so if we look at a couple of sound waves here, this kind of illustrates the idea of amplitude. So a typical sound wave is going to be represented by a sine wave, as you're seeing here, and the distance between the crest and the trough is going to be your amplitude. Okay, so if a sound wave has a longer distance between its crest and its trough, it's going to have a higher amplitude, and then a sound that has a low amplitude is going to have a very short distance between its crest and its trough. A sound wave's amplitude is going to decline in intensity the further it moves away from a source. So if you're very close to something making a sound, obviously it's going to be louder than if you're very far away. In interior spaces, sound waves reflect off of things like walls and ceilings and floors, and the reflected sound waves combine to produce a consistent sound level. All right, so if you think about being in a space where there's a lot of people gathered and everybody is talking, all of those sound waves are coming out of the people's mouths. They're bouncing around the space all over through or off of all of the different surfaces within that space. And then all those waves, they're going to be converging together and producing sort of a consistent noise level. All right, so when you think about just the chatter that you would be hearing in that space, that's just all those sound waves coming together. And when that happens, you're hearing so many sounds from different sources. Individual conversations sort of become indistinguishable. Okay, everything just sort of turns into a consistent level of noise throughout the space. When sound waves bounce off of surfaces, the amount of time that the sound wave exists will increase. So if a space is filled with hard surface materials, sound waves will bounce more and more, and the sounds will last longer. Okay, so like if we're in a warehouse or something like that, the sound within that space is going to last a lot longer than if you were in just a bedroom in your house, obviously, because for one, the space is a lot smaller, but there's a lot of hard materials in the warehouse as compared to your bedroom, right? And the softer materials are going to absorb more sound than the harder materials. As sound waves reflect off of surfaces, they accumulate as reverberations. So reverberations can be defined as the persistence of sound after the sound source has been stopped. All right, as interior designers, we want to prevent sound waves from bouncing around within spaces, and we will accomplish this by specifying materials that absorb those sound waves. And we're going to talk about that more in depth a little bit later on, but especially going into next chapter. That's kind of what next chapter is all about. So a reverberant field, this is an area that is prone to sound wave reflection. So this diagram here I stole from later on in the chapter in the textbook. You're going to be seeing it pop up again, but I decided to throw it in here because This kind of shows an example of a reverberant field. So you just have two people within a space, an interior space, and the sound within that space coming from the source wants to bounce around all over all of the different surfaces. Okay, this is opposed to a free field, and a free field is an area free of reflective surfaces. Okay, so think of like being out in the middle of nowhere outside in the wilderness. There's nothing around you to sort of bounce waves around. Sounds generated within a free field moves outward in all directions. So it's going to start at the source and move outward in all directions, and then gradually it's going to diminish in intensity the further it moves from the source. Okay. Again, I kind of stole this from later on too, but this is sort of an illustration that effectively represents what we're talking about here at the free field. So you have your sound source at the center, and then it's producing sound, and then as that sound is produced, it's equally going to be distributed in all directions. Okay, so it's radiating out in a circular format, and then as it gets further and further away from the source, it's just going to diminish in intensity the further it gets away. All right, so looking a little bit more in depth at sound waves, these are often represented as sine waves that depict an energy change from positive to negative. Okay, so if we look at our little diagram here, the line that's going through the center, that's sort of representing our baseline. So you can think of that as 0. Anything above that line is going to be a positive, and then anything below that line is going to be a negative. Okay. A wavelength, this is going to be the distance between the peak of one sound wave to the peak of the next sound wave. It is the distance a sound travels in one cycle. Okay, so again, looking here, our wavelength, you can see we have a peak here and then a peak here. The distance between those is going to be the length of the wave. Frequency, so when you hear the term frequency, this refers to a sound's pitch. So that's how high or how low a sound is, and this is going to be measured in hertz. High-pitched sounds have a higher frequency, and lower-pitched sound, and they also have shorter wavelength, while low-pitched sounds have lower frequencies and they have longer wavelengths. Okay, so a lot of technical stuff in this chapter. The textbook goes a lot more in detail on these, so kind of read through them and understand them, but a lot of this honestly relates back to probably some of the science courses that you've taken previously, whether it be in high school or even in college. If you think back to sort of light and light transmission, there's a lot of things in common between light and sound in terms of wavelength and frequency. Okay, a lot of those terms carry over and they have the same definitions. So now we're going to talk a little bit about hearing. Okay, so humans can hear sounds in the range of 20 hertz to 20,000 hertz. However, this range can vary between individuals and it's impacted by age. Okay, so obviously if you think to your parents, maybe you've done a sort of sound test in the past where you've played a high-pitched sound for them to see if they could hear it. That's sort of exactly what this is talking about here. As we get older, our sound or our ability to perceive higher frequency sounds is going to degrade. But the common range that you will hear in your lifetime is going to range between 20 hertz at the very low end to 20,000 at the very high end. The human ear is most sensitive to mid-range frequencies. The best sensitivity is going to occur between 500 to 6,000 hertz with a maximum sensitivity at 4,000 hertz. Okay, so any sound that has a frequency between 500 and 6,000 hertz. That's going to be very easy for us as humans to perceive. Anything above or below that, it's going to be a little bit more of a struggle. Our ability to hear upper frequencies decreases with age. Okay, like I said, by middle age, the upper limit ranges from 10,000 to 12,000 hertz. Okay, so already by middle age, that's like 8,000 less hertz than you may have been able to hear before. So kind of depressing, but that, that's just what happens as we get older. Many animals, including dogs, can hear ultrasounds. So ultrasounds are sounds with ultra high frequencies or ultra low frequencies, things that humans cannot perceive. Okay, so these sounds have frequencies, well, I just said, too high for humans to hear. So if you think of like a dog whistle, obviously, humans cannot hear that, but a dog can, and they react to it. All right, loudness. So the term that you will hear when people are talking about how loud a sound is, the common term that's tied to that is decibels. Decibels are units that express sound intensity on a uniform scale from 0 decibels to around 130 decibels. So at 0 decibels, that is sort of your baseline for the quietest sound that is able to be perceived by a person. Okay, so the absolute quietest, you can make something, but somebody can still hear it, and they're aware that the sound is there. Okay, 130 decibels, that is the upper end, and that's going to be the threshold at which the sound starts to impact your ability to feel pain. Okay, so that's when it actually starts to hurt your ears, when it becomes that loud. Okay, so that's the range of the decibel scale. If you look here at the sample decibel levels, this is what they give you in the textbook. So the threshold of hearing at the very bottom, that would be like a leaf. Well, no, a leaf would be 15. That would be like you're hearing a feather brush against something, I guess, is what they're equating it to. Like very, very quiet. You can almost not even hear it at all. And then at the high end, you're going to have something like a jet engine that's taking off, something so loud that it's starting to actually hurt your ears. Okay? Sound masking, this is a phenomenon that occurs when two separate sources of sound are perceived simultaneously, and at that point they will be obscuring one another. So as interior designers, sound masking is something we can actually use strategically, and this allows us to ensure speech privacy, reduce stress and absenteeism, and create a better work environment. So one way that you could incorporate sound masking into a design is finding a way to introduce ambient background noise to cover or mask any unwanted noises. Okay, so if we're able to hide things that people don't want to hear, that's going to help them focus better and be more productive. Okay, so that's something we want to take into consideration when we're designing. Sound sources, so sounds within a building, interior can come from a lot of places. Below are a few common sources. Obviously human speech, people just talking to one another within the space. Maybe there's music playing. Mechanical equipment, all right, so we've talked about mechanical equipment with our last module, but all of that equipment that is within the building will produce noise, okay? So it might vibrate, and those vibrations will carry through the entire system, and if they're in contact with any solid materials like flooring or ceilings, that sound can be transmitted through those materials into the space, and we can actually hear it then, which could be annoying. So that is a source of maybe some unwanted sound within the space. And then also noises from outside, such as cars on the street. All right. A noise is simply defined as any sound that is unwanted. Okay, so sound and noise a lot of us might think those are synonymous, but there's actually a difference. A noise is actually just like an annoying sound, something that you don't want in a space. So a noise would have a negative connotation with it. The classification of a sound as a noise is subjective, and that's going to vary from person to person. So maybe, I don't know, something is playing. Maybe it's a song, and one person likes it, and they might consider that a sound, but another person thinks it's a really annoying song and they don't like it, so they would consider it noise. You can think about it that way. It's subjective, and a noise for one person may not necessarily be a noise for another person. All right, sound paths. So sound waves travel through different mediums at different velocities. So for example, sound is going to travel through air at around 1,087 feet per second, and then it's going to travel through water at about 4,500 feet per second. So this is actually kind of interesting. This isn't what I would have thought, but sound will actually travel faster through water than it will through air, which is kind of cool. Attenuation. So sound can be absorbed or reflected by objects. Obviously, we know about that. That's why we're talking about acoustics in the first place. But attenuation is basically a measurement of the decrease in energy by means of absorption, scattering, or spreading in 3 dimensions. Okay, so when you hear the term attenuation, it's talking about how much is the energy of the sound being decreased by either absorption or scattering or spreading. Reflected sound, so harder, more rigid surfaces reflect sound or more sound than softer, less rigid surfaces. For example, a concrete floor, that's going to reflect more sound than a carpeted floor. Reflected sound leaves a surface at an angle that is equal to the angle at which it strikes it. So here's that same diagram I mentioned previously. But if you look here, we have a bunch of different angles that the sound is striking these walls within this space. And if you look at any of these angles, the angle at which the sound strikes the surface is going to be equal to the angle at which it leaves the surface. So here, for example, this is forming a perfect 90-degree angle because the sound is hitting the wall at a 45-degree angle, and then it's going to be leaving the wall then at a 45-degree angle. Reverberation, so I mentioned reverberation sort of at the beginning. This is the persistence of sound after the source has ceased due to repeated reflections. All right, so what this is saying is the sound source has stopped, but the sound waves are still bouncing around the room, and that is causing the sound to stay active even though the source is not producing sound anymore. So it's kind of like an echo. An echo is a little bit different, but for interior spaces, whenever you're thinking about like an echo or a sound bouncing around, that's going to be reverberation is the term for it. Reverberation time, so this is the amount of time it takes in a particular space for a sound to drop a total of 60 decibels. Reverberation time is directly proportional to the volume of a space, and it's inversely proportional to the absorption of surfaces. So as a space gets larger and there's more volume in that space, the reverberation time is going to go up. Okay. Spaces without acoustical treatments have longer reverberation times, while spaces with acoustical treatments have shorter reverberation times. Reverberation times within spaces should be controlled at a level that is appropriate for the function of the space. So reverberation time is not necessarily a bad thing. It can actually be used strategically in certain scenarios. So, for example, if you had a space like a lecture hall, a theater, a place of worship, or a concert hall, you might want a longer reverberation time in that space because that will help the sound within the space sound smoother and richer. If this were if you're designing just like a regular space, like an office environment or maybe like a residence, you would want shorter reverberation times because those help to accentuate speech. Okay. And then here we have a diagram from the book, which is kind of showing how reverberation works. So we have our sound source. Let's say this is like in an auditorium or something. The sound waves are coming out and they are bouncing in all directions. And then they're bouncing to where the people are so that they can actually hear it. But you would want to have some acoustical treatment in this space so that the sound waves aren't bouncing around too much, because if that happens, then it becomes very difficult to hear what's actually going on, because the reverberation at that point just becomes so intense. So kind of what happens if you're in a space that's not acoustically treated very well. Think of like the studios in the new building. I call it new because it was new when I was there. But if you try to get work done in those studio spaces, it's very difficult sometimes because of the lack of acoustical treatment within that space, okay? Like, for example, when I was there, I almost never worked in the studios when I had the chance to just go home and work, because the amount of reverberation going on in that space, there's concrete flooring, there is the glass windows, there's the glass curtain walls where you have those meeting rooms. There's a little bit of carpeting, but then, I mean, there's not really any soft furniture. You have the desks you're dealing with. So any sound within that space is going to bounce around like crazy. And then when you're dealing with the reverberation, which is basically the persistence of the sound to keep going, right? It's like an echo. I can say something and that sound keeps bouncing, and then I keep talking. Then you're mixing what I've said in the past with what I'm saying now, and it makes it very difficult to hear, right? Because there's nothing catching that sound and stopping the old sounds from continuing to bounce around. So when the old mixes with the new, that's what causes things to become confusing and you can't really understand what's going on. And also it's noisy, right? You're having all that unwanted noise bounce around, which makes it difficult to focus. So moving on, diffusion. This is the process by which sound waves spread after reflecting off of convex surfaces. So if we have a surface that is bending outward and we have a sound wave that's bouncing off of that, you can see when the sound wave is going to hit that surface, the curving nature of the surface is going to cause those sound waves to spread out sort of in a radial form, or a radial pattern, right? So you sort of have like a direct line from the source to the surface, then it's hitting it, and then it's just spreading out in a bunch of different directions and going all over. The opposite of that is known as focusing. So this is when you have a concave surface and sound waves are hitting it, and then when they do that, that causes the sound waves to converge at a single point or focus at a single point. So you can see here we have our source, it's bouncing. Then those sound waves are converging with one another when they're getting to the person who is then hearing them. Diffraction. This is a process by which sound waves pass around obstructions and small openings. All right, so if you look here, what we have is our sound source, and then we have a wall with a tiny opening in it. All the sound is coming out of that, and it's bouncing around in here. And then since we have a tiny little opening within that wall, obviously some of those sound waves are going to be making their way through. So diffraction facilitates the ability for sounds to be heard beyond a barrier, right? Whenever you can hear sounds from one room to another, diffraction, that's the term that is associated with your ability to actually hear what's going on in another room. And for example, diffraction through a keyhole is something that's very common. So if you have a door and you have a keyhole there, sound will be making its way through that keyhole into another space, and that would be an example of diffraction. All right, so the last thing we're going to talk about in this lecture is absorbed sound. Okay, so the amount of sound that is absorbed by a surface depends on the area and the absorption characteristics of that surface's material. No material can reflect or absorb sound perfectly. Any material will always both reflect and absorb sound. Okay, so if we had a highly reflective material like polished concrete as our flooring, or even like glass, something like that, even though it is very reflective and is not going to capture a lot of sound, there's always going to be some sound that is being absorbed by it. Okay, and the same is going to go for something that is highly absorptive, like upholstery or carpeting. Any sound that's hitting that obviously is going to be reflected back. Okay, so it's going to be absorbing sound a lot more than something that is very hard, but it's still going to be bouncing some sound around in the space. It's neither one can be perfectly reflective or absorptive. Different materials also handle high, mid, and low frequencies in different ways. Because of this, interior designers should be aware of the frequency levels that will be present within a space so they can select the most appropriate material for absorption. All right, so when you're designing, obviously you're going to know the functionality of the space you're designing for, and that will give you an indicator as to the frequency of sounds that will be present within the space. So if it's like an office, which I like to keep going back to, that's probably going to have a lot of mid-range frequencies. And then if it were a theater or something like that, or like a concert hall, that's probably going to have a broader range of frequencies. So you're going to have mid-range, you're going to have some low ranges, and you're also going to have some highs mixed in there. So there's a lot more of a range with a space like that. But that will give you an indicator as to the type of materials you'll have to put into the space to get the best sound control. So thicker materials are best for absorbing low frequency sounds, and then deep porous upholstery would be good for absorbing mid to high frequency sounds, okay? And this is sort of just an intro to those, but we're going to get more in depth with them next week, going into actual applications and design considerations. And then lastly, the absorption coefficient. So this is actually the way we measure how absorptive a material is, how good it is at controlling acoustics. So this is the ratio of sound energy absorbed to sound energy reflected by a material. So how much sound is that material trapping in versus how much is it reflecting back into the space. The absorption coefficient depends on the frequency of a sound, and it also depends on the sound's angle of incidence. So that is the angle at which the sound is striking the surface, okay? Any change in those two factors will have an impact on the actual coefficient measurement for the material. And then here at the bottom, we just have a table that was provided within the textbook. So this is going to show you the sample absorption coefficients of some of the basic building materials that you'll be running into as you're designing. But this table is really nice because it breaks all these materials up based on frequency. Okay, so you can see here on the left we have lower frequencies, and then here on the right is going to be higher frequencies. And this allows you to see how each material performs with those different frequency values. All right, so anyway, that's going to do it for this week's lecture. As always, if you have any questions about anything or need help, please reach out to me and ask, and I will get back to you.